Hello, y'all. Darrell Lee Berry Jr. here, back with some more science impromptu session. I'll be doing some thermodynamics problems in preparation for my exam on Wednesday. So I've already gotten through just about half the problem. So I'll see how many more I do in the time frame I have. I'm undecided whether I'll get lunch or not. So I may take a break and get some lunch and then come back, which is probably what I'll do. So I'll probably be here about 30, 45 minutes at the most. We'll see how it goes. I'm actually sleepy because I was up all night working at my other part-time job. So, oh, see what I mean? Forgetful. Put my pen down somewhere. So we'll see how far it goes. But right now I'm on what number am I on? Yeah, I've finished chapter 4. So maybe I shouldn't have put heat engines because technically that's over. Maybe mostly Gibbs and uh free energy and such. Let me make that change. I think I just did the last heat engine problem. Get into some more difficult things. You're not even Perno. But Gibbs, some things in these problems. Compressibility, Gibbs, um, what? That's good enough. All right, so here we go. So these are the ones that I plan on doing before 5 o'clock. I have a study session with my mentee. This is not my tutoring student, but I'm a mentor as well for a undergraduate student that just transferred, and he's actually in my thermal class. Technically, you take a thermal class earlier in your academic career, but it just wasn't fitting my schedule. So I'm taking it as a senior, which is common enough. I mean, the class is like it runs the range of freshmen all the way to seniors. Uh, so we'll meet today and talk about these problems. So I'm running through them. So let's start with the chapter 5 problem and see what we have. Let this system be 1 mole of argon at room temperature at atmospheric pressure. Compute the total energy. I remember this one. Kinetic only, neglecting atomic rest energies, entropy, enthalpy, Helmholtz, and Gibbs. Oh my gosh, so this program covers them all. Let me actually type all of these in. Uh, and these will be sort of hit back as we go along. So we have entropy, enthalpy, Helmholtz. This is the one I was trying to remember, but I think the sleepiness was getting the best of me. Helmholtz, Gibbs. All right, seems good enough. So why don't let's go through this thing. So we have a mole of argon. So N equals 1. Argon gas has this atomic, what do you call it, name. And I'll go to my trusty periodic table that those who've been following me for a while are familiar with. I've shared it a few times, I believe. And argon has atomic mass of 39.948. And this is going to be for a mole. So we do have 1 mole. So 1 mole of argon is 39 grams per mole. And the system is 1 mole. All right, so that's easy. The gas is at room temperature, which we'll call, technically it's 298, but we'll call it 300 to have an easy number, 300 Kelvin. And atmospheric pressure, so 1 atmosphere. And I always forget what the temperature conversion is. Let me look it up in the back of the book. Oh, maybe I should share the book, shouldn't I? Scrolling through it. I'll get the book into share again. I guess I didn't. I believe is e to the 5, 10 to the 5 uh, newtons per meter squared. It's loading, it's updating or something. And atmospheric pressure. So is one of the common equations. Let me share my Kindle. So this is an equation that we looked at before. I always forget the name of it because it has a funny name. Here it is, the Sackur-Tetrode. So we'll use the Sackur-Tetrode equation for this. So entropy equals N, the Boltzmann constant, the log, the natural log of the volume divided by the number of particles times 4 pi the mass, the energy over 3 n h squared to the 3 halves plus 5 over 2. And this will give us the entropy of an ideal gas. And we have pretty much everything we need. We have 1 mole, so we know it's 39 grams. We need to put this into kilograms. So this is 0.039 kilograms per mole. The energy will be by the get the name of the equation. It should be that related to the energy. I will load that equation. Or at least I'll type that equation. But this would have saved by now. It's on my old formula sheet, so let's pull that one up. So when we have a gas that's diatomic, no, it's monatomic. So F equals 3. This is basically the degrees of freedom. And the equation I was thinking about is this one. Thermal, the energy, is going to be the number of particles times the degrees of freedom times 1/2 kT. So we can use that to plug into this U right there. And we have the ideal gas law, PV equals nRT, which is big N KT. And I'm not sure which one is better to use. Say NKT, since we can cancel out an N. So I will say that PV over N equals KT, and thus V over N equals KT over P. So now we have simplified this equation a bit. So let me fill out what I mean. We have the entropy is NK ln. Instead of V over N, I'm gonna put KT over P. This is still 4 pi m. And now we have, I'm gonna fill this in. The U is gonna be NF 1/2 KT. So that's saved. Then we have 3 NH squared. That's going to be to the 3 over 2 plus 5 over 2. And thanks for joining. Who joined? Let me know if you have any questions. So, doing some complicated enough problems at the moment. So, probably a bit more involved in like the normal science hour program, but you'll be able to follow along with some exam preparation. So I believe I wrote that properly. V over N, KT over P, 4 pi M. Plug this in F 1/2 KT, 3NH squared. Okay. And we can see that this N cancels, and I guess that's the only thing that cancels. Awesome, Bronx. Thanks for letting me know. I appreciate it. It does motivate me to continue when I know people are watching, people appreciate it, so thank you. So this is going to be NK ln KT over P, 4 pi M. And actually this 1/2 times 4, I'm going to make this a 2. F KT over 3H squared, 3 over 2 plus 5 over 2. And I'll see if I can simplify this a bit farther. So everything inside this parentheses has 3 over 2. I'm gonna copy this real fast. So normally I would just plug this in, but I'll see if I can show you all a bit further simplification. So everything inside parentheses is 3 over 2, and everything here is 2 over 2. So let's see what happens if I combine some of these. So basically this will be, if I take this t out, that's t 3 over 2 times t 5 or 2 over 2. So this should actually be t5 over 2 if I take that t out. And is there anything else I can take out? I don't think so. So that might be it. Everything in there, and therein is ln. There's one other thing that I can do that I saw happen in one of the textbooks or the problem the solution set. But I could turn this 5 over 2 into a log as well. So I can say 5 over 2 equals ln e 5 over 2. So now we have n k ln k. Oh, I forgot about a k that was right there. So this k will also be 5 over 2. If I take the k out, there we go. So we have ln k 5 over 2 t 5 over 2 over p. And this is going to be 2 pi mf over 3 h squared. That's to the 3 over 2 still. And now we have plus ln e 5 over 2. Apologize, maybe this should actually be mixing it up. Nope, that's right. Because this will end up being, when you have an exponent inside of a logarithm, this ends up being 5 over 2 ln of e, and ln of e is 1, so it ends up being 5 over 2 again, so that should be correct. And now I have logarithms that are adding, so when logarithms are adding, you can multiply them, the stuff that's in the middle. So we have nk ln of e to the 5 halves. Oh, this simplifies things. So we have e k t. All of these are to the 5 halves divided by p. And then we have 2 pi mf over 3 h squared to the 3 halves. And okay, that should be good enough. I'll type this in and see if I got it right. And these are all problems I did before. Like this was the homework that was due recently. So I'll be able to pull up my old homework and see if I got it right. But as long as I'm close enough, I'll be fine. As long as it's not like a crazy number. So you do lose points on an exam if you like off on the number, but as long as you get the understanding right, that's the main thing. Actually, let me type out the number so it's clear what I'm typing in. So this number here, N, is Avogadro's number because I have a mole of particles. So that's 6.022 times 10 to the 23. And this is Boltzmann's constant, which is it's a 6 point. I can actually take off one number of accuracy on that. Boltzmann constant, where do I have that at? Oh, there it is. So so now I need to make sure I have the right units when I plug this in. Boltzmann constant is J over K. I have K, so that should be good. We have 1.381 times 10 to the negative 23 joules over K. Ah, thanks, Bronx. And what's going on, the mathematician? Yep, this is live. And this is not the one that's going to be this evening. I'm just basically studying for my exam. Like I was telling y'all, I have the thermodynamics exam on Wednesday, so I figured I might as well do some on the stream. Yeah, but this is an extra stream. I'll do more complicated stuff than what I normally do on the you know, hour mathematician. So it might take a bit longer, but hopefully y'all find it interesting. But this is like how I prepare for my thermal exam. I did this for the last one, and did pretty well. I made like a 88, which is good. And then I'll be able to do a redo on the problems that I missed and get half the points on them. So I should end up with like a 90 something when all is said and done. Thank you. I appreciate it, the mathematician. Thank you for being a good sport and passing the word as well. So yeah. So we'll see. We'll see how, because I've actually been pretty busy recently, so I don't think I prepared for this one as much as I normally would ahead of time, but I did start on the homework really early. So I still have a lot of time. Like I'm already getting through the whole homework. And I was telling Bronx earlier and those who were here earlier how I'll be meeting with my mentee later today and we'll review these problems. So I want to make sure that I review all the problems as much as I can. Like I was telling you, mathematician, I'll try to review things ahead of time so I could help cover them better. Yeah, I hope so. But I mean, overall, my score is good in the class. So even if I bomb this one, or maybe not bomb it, but even if I didn't get an A on it or something, I can still get an A out the class, I'm sure. But yeah, I think I'll get at least a B. That was just the NK at the front. Now the LN, we have. Yeah, hold up. That's right. I forgot I did that simplification that I don't normally do. So I put the epsilon in there. I mean the E. So this is another 1.381 times 10 to the negative 23 joules over Kelvin. And I picked the temperature of 300 Kelvin. And this is going to be over the pressure. I forgot to look up the pressure. Uh, yes, it's 10 to the 5 newtons per meter squared. I am starting to remember that. That is what I wrote, right? Yeah. So 1 atmosphere is 10 to the 5 newtons over meter squared. So do I have enough room to write this in? Yeah, 10 to the 5 newtons per meter squared. And only the top part is to the 502, 5 over 2. So this is to the 5 halves. And I do need to actually shrink the size of this a bit. This is going to all be multiplied by 2 pi, the mass we got for a mole of this particle in kilograms, is 0.039 kilograms. It's a monatomic gas, ideal gas, so the degrees of freedom are 3. And for 2 pi m, then we have 3. And then we have h bar squared, or just h. I keep saying h bar because I'm doing quantum. When you do quantum, you start thinking about it in terms of h bar. So uh, h is the Planck's constant, and it's some number, small number. And h bar is h divided by 2 pi. So in quantum mechanics, it's usually h bar. It's just the way subatomic particles work. Like all of these constants, they're constants for a reason because they relate to very definite and consistent properties of the universe. So you will find that when you measure an atomic particle, for instance, its size will be some proportional to that constant, for instance, something like that. So there's always some kind of relation. So without the bar, that's 6.626 times 10 to the negative 34 joules times seconds. And this is all to the 3 over 2. All right, so that should be it. Let me see if there's any questions came up. The mathematician, can you show me your grades after this? Um, I mean, technically my grades are already online. Right now I have a 3.6, um, which is pretty good if I say so myself for UT Austin. UT Austin is a pretty difficult school. So my overall GPA is a 3.6. Bronx says, it seems like no matter how complicated the equation is, as long as you follow the rules of math, it can get broken down into something more manageable. That is true. And some professors even take points off if you try to uh, not break it down. I've heard of that. I never had a professor like that. Uh, but I can tell you one thing though, if you don't simplify it, like one of the things I notice with the students I work with in class as a learning assistant, they will start with an equation like this and they'll put the numbers in like here. Like they will immediately plug the numbers in and they may even try to do all the simplification with the numbers in. And that never ends well. So you want to try to simplify as much as you can symbolically, and then at the very end, put in all the numbers, and then you can just type it into your calculator. So that's generally the best way to do these things. And mathematician says, it looks like there is chemistry in this problem. This is complicated. Yes. So Avogadro's number, a mole, all of that stuff. So the higher you get into physics, the more you find that things are related. Like in my quantum 2 class, even though it's quantum mechanics, we talk about chemistry almost every day because you're talking about subatomic particles, you're talking about electrons, and chemistry is all about electrons. If you think about it, what makes an element? How many electrons are bound to how many protons and neutrons? The atomic number is the number of protons and neutrons, and that's going to, give rise to the spin. All of these things come into place. So yes, moles, uh, uh, entropy. Even though I guess they don't talk about entropy so much, but Gibbs free energy. They talk about that a lot in chemistry because that determines whether a element, a molecule is going to form naturally if the Gibbs energy is low. Mathematician says, "Am I the smartest person in class?" No, I am not actually. I'm just average at UT. In my community college, I was the smartest person in class because I got a 4.0. Like I graduated summa cum laude. That's the highest you can get. So in community college, I literally graduated with the highest grade you can possibly get. Twice. I got 2 associate degrees. But when I came to UT Austin, I'm just average here. Everybody's smart. You can't get into the school unless you're very smart. So I'm just average here. It's crazy how it's connected. Yes, it's pretty cool. But it's why we have technology. Because the more you get into technology, all of these things, if they didn't work and all interconnected where they do, so many things we wouldn't have. Like right now, there's optics with the camera, there's EM with the capacitors and stuff like that. There's thermodynamics with the power plant that's powering everything. The chemical compounds that go into making the stuff, that's chemistry. I mean, there's just is all interrelated. All right. So I think I procrastinated enough. I'm going to type these numbers in. Let's see what I have. I did a few things I don't normally do, so I might have made a mistake somewhere. Let's see. So 6 times 10 to the negative 23, or 10 to the 23. We have 1.381 to the negative 23 joules over K. Oh, gotta watch my units. To do everything right on my units. Okay, I'm just gonna type it in. I'm just gonna assume the units are right. So we have uh E is E times 1.381 times 10 to the negative 23 times 300. Oh, and all of this is to the 5 halves. Then this is going to be times 10 to the 5. Right? Then all of this is going to be times in the numerator. Is that 2 pi? Yeah, it is a pi. It's going to be 2 pi times 0.039 times 3. That just made that 6. And then in the denominator, we have 3 times 6 point, oh, and I got to square this. So parentheses, 6 times 626 times 10 to the negative 34. All right, should have that put that in parentheses? Got to 3 halves it. So this is 3 halves. Sees the other side. So we got that. And I think I got to put a parentheses on the outside to close everything in. Ah, it's off by a bit, but so I got basically 115 for entropy. I know that's wrong. That's not exactly right, but it's close. It's close. But on the exam, I don't do experimental stuff. Like on the actual exam, even though it's harder to type all the numbers in, I probably would type the numbers in here on the actual exam. I'll probably type it in right here. And even though I end up typing T more than once, even though I have a +5, 2 at the end, normally I would just type it in here, but I did some experimentation. And mathematician says you should subscribe to this channel because he solves interesting problems like the refrigerator, which is very interesting. Awesome. Thanks for saying the mathematician. And it's that TI-84. Yes, that is correct. So this is the one that I have, and I like it. It's pretty good. It actually has Python in it as well, even though I haven't used the Python function yet. Even though I'm learning Python and I do Python, I did my research in Python, but it is that. But suffice it to say, I'm pretty sure this is a questionable number. It's a bit off. I probably typed something in incorrectly, but I mean, it's not like crazily unreasonable. So I'm going to just move forward with this problem. So now we need to get so that was the entropy. Now we got to get the enthalpy, which I don't remember how to do. Let me see what I did last time. I'm going to bring up my old homework problem and see what I did. Matter of fact, I might even just go ahead and copy my answer from the last time I did it for the entropy as well. So whatever typo I made, I'll just make sure to not do that. It probably was the E thing I did, which I don't normally do. I'll make sure not to do the E thing next time. Oh, and then my quantum class. I've been doing quantum homework, which was due recently. Maybe if they can open up quantum first. This is the stuff I'm gonna really have to think about on the exam. Uh, the enthalpy stuff. This is basically the stuff that deals with why things form, like why is diamond naturally, why is diamond not natural on the surface of the Earth? It's because the pressure and the Gibbs free energy uh, uh, is lower at higher pressure. Therefore, you have to have a high pressure to form diamond, and graphite, I believe it is, forms on the surface of the Earth because of the Gibbs free energy. All right, terribly off actually. So in the homework that I did when I actually did the problem earlier, I got 154.83. So I mean it's not horribly bad, but I'll go ahead and work with this one now so that I get pretty much the same answers before. That was the entropy. Now, in order to get the enthalpy, enthalpy equals U plus PV. And I'm keeping track of these formulas. If you see me convert them every once in a while, that's because I'm going to go back. The professor lets us make our own formula sheet. So I need to keep track of the formulas I have to use to solve these problems so I can make sure that they're on my formula sheet properly. May actually have to go back and catch a few if I miss some. So entropy has to do with a certain type of heat that that I have to look up to give you the details. I don't remember the details of entropy. And Bronx says, if you meant me, I've already subscribed to Barry. As a black man, I want to support my fellow brothers and sisters who don't get the algorithm love. Thanks, Bronx. I appreciate it. Yes. So my goal is to get 1,000 subscribers by what? By December? I think that's a reasonable goal by December. Get 1,000 subscribers. So hopefully I get there. So we're going to solve for enthalpy. Now we already have U. We got U earlier. I just didn't solve it separately. When we solve the equation for U, we just got to get the pressure and the volume. All right. So looking at what I did before, we already have U. We have the pressure, so we just need to get the volume when we can solve for enthalpy. This is enthalpy. And maybe I should look it up, by the way, to remind myself, since I can't actually tell you the definition right now. Let's search entropy in the textbook and remind myself what enthalpy is. Okay, here we go. So and remind me, by the way, if I forget to, sometimes I forget to move the everything back over the way it was so you can see it on writing. Let's take a look and see what enthalpy is. So enthalpy, constant pressure processes occur quite often, both in the natural world and in the laboratory. Keeping track of the compression expansion work done during these processes gets to be a pain after a while, but there's a convenient trick that makes it a bit easier. Instead of always talking about the energy content of a system, we can agree to always add in the work needed to make room for it. So what they're saying is, and you can see this bunny right here. What they're saying is, if you want to create a bunny out of nothing, like if you want to just use magic to create a rabbit, first you're going to need the energy of the rabbit. So E equals mc squared, and we're going to call that U in thermodynamics. So you need the actual energy of the mass of the bunny, right? But at the same time, before the bunny was there, there's air there, and you have to push the air out the way to make room for the bunny. So this is going to be U plus PV to make room for the bunny, and they call this H. So H is going to be the energy both to make the object and to move the air out of the way for room for the object. And this is relevant because um, let's say we utilize, is it electrolysis to make whatever the process you utilize to make water from hydrogen and oxygen, right? So you have a whole bunch of oxygen floating here, and you have a whole bunch of hydrogen floating here, and you put them together to make water. Well, the water is going to be one little drop like this. With the oxygen and hydrogen, all of this oxygen and hydrogen goes into that. So what that means is when you form water, air, air collapses into that space, and that gives us energy. And that's how some batteries work. I believe it's a hydrogen cell is when they make water out of the hydrogen and oxygen, the collapsing space extracts energy from that space that was there. If I'm understanding it properly, keep in mind I'm learning all this stuff, so once in a while I might mix up a concept or something, but that's a general idea that there's energy to hold the atmosphere away to keep that oxygen and hydrogen there. And when it collapses to form water, we can extract the energy from the atmosphere collapsing. That's the PV. So this. I mean, it's not just a function that people are using or some kind of equation that people made up. This is relevant with real processes that we utilize every day, even though you don't always realize it. So we have U, we have P that was given. TV equals nRT. So we can say that V equals nRT over P, which is going to be 1 mole, and R is going to be, what do we get for R? Oh, there it is, 8.31 uh, joules per mole Kelvin. And we have the temperature. I picked 300 Kelvin. So we have 300 Kelvin for temperature divided by 10 to the 5 newtons per meter squared. So let me take a look and see if there's any questions while I'm typing this in. And all right, awesome. The mathematician, I'll see you tonight. I have a metaphysical discussion tonight. So I'm going to type this in and see what the volume is. We have one. Oh, and it's almost time to leave for lunch. So I'm going to finish this step of the problem, and then I'll catch the cafeteria before it closes. But I shall be back. 8.31 times 300 divided by 10 to the 5. Okay, so the volume is only 0.02493, and there should be atmospheres. Let's see. No, it's not atmospheres, it's meters cubed. Let me show you this really fast. This is important. So you have a mole cancels a mole. You have a Kelvin cancel a Kelvin. So what we end up with is joules divided by newtons divided by meters squared. So this is going to be joules meters squared divided by Newton. Now, joule is newtons times meters. So this is going to be newtons times meters over newtons times meters squared. So that means that this is going to be meters cubed. So that means that this is 0.02493 meters cubed. That's the volume of this air. So now I can calculate the enthalpy, which is the total energy needed to both make this gas out of nothing and push the air out of the way to give it room to exist. And so this is U plus PV. And remember, U is, I had that formula earlier. I'll just copy it. And just in case I don't forget, let me make it into a formula to capture. Not pretty, but I'll see it. So we know U is this plus PV. So we have 6.022 times 10 to the 23 number of particles. The degrees of freedom are 3, 1/2. And then we have K again, which is 1.381 times 10 to the negative 23 joules over Kelvin. And then we have 200, and actually I put it 300 Kelvin in the homework. I was actually more accurate, 293 plus times 10 to the 5 newtons per meter squared and times 0.02493 meters cubed. All right. And if we look at this, we have Kelvin's going to cancel, so that's going to give me joules right there. And then we have meters squared cancels in meters, and again, Newton's times meters is joules, so the units are right. So it's always good to check units. So we have 6.022 times 10 to the 23 times 3 times 0.5 times 1.381 times 10 to the negative 23 times 300 plus 10 to the 5 times 0.02493. All right, so that gives me a Gibbs, an enthalpy. Enthalpy equals 6,235, which is reasonable, joules. So that's reasonable. So if you were going to make this gas out of nothing and give it a place to live, E equals mc squared plus the energy of that it takes to hold the atmosphere away to keep it there is about 6,000. In the homework, I got 6193. In the homework, I used actual 298 for the actual temperature for a room, but here I'm rounding a bit, so chance of reason it'll be a bit bigger. So awesome. So I'll be back later. I'll do some more problems. So I'm meeting my mentee at 5. So I plan on getting through as many problems as I can before 5 o'clock. So I can meet him having gotten through most of the problems. I did the practice exam earlier and chapter 4 problems, and now I have these. What, 1, 2, 3, 4, 5, 6, 8. 1, 2, 3, 4, 5, 6, 7. Yeah, 8 more problems. So I'll get something to eat, and then I'll be back, and I should be able to get the rest of these 8 problems done. So awesome. So thank you for showing up, Brox. Thank you for showing up, the mathematician. Hopefully you all enjoyed. You could see the joys and pains of getting a physics degree. And I'll see you all later. Thanks again for joining, Brox. Thanks for dropping the line.